You check your phone. GPS says you're 230 feet from where you actually stand. Your tractor circles in the field like it's possessed. The northern lights glow red over Texas. Your power grid just died. 6 million people sit in darkness. And 93 million miles away, the sun just sneezed. This isn't science fiction. This happened in Quebec in 1989. It happened to American farmers in May 2024. And the mechanism behind it is so strange, so counterintuitive, that even engineers designing our power grids didn't see it coming until transformers started melting. The sun doesn't just give us light and warmth, it throws tantrums. Magnetic fields on its surface twist like rubber bands until they snap. When they do, the energy release equals 1 billion hydrogen bombs going off at once. That's a solar flare. But here's where it gets weird. The flare itself isn't what kills your technology. The flare travels at light speed, 8 minutes from sun to Earth. You can't dodge it, can't prepare for it. By the time you see it happen, it already hit you. But that's just the opening act. 17.6 hours after English astronomer Richard Carrington watched a white flash on the sun's surface on September 1st, 1859, Earth's magnetic field went haywire. Telegraph operators got shocked. Papers caught fire from sparks shooting out of machines. The aurora borealis lit up skies so bright over the Rocky Mountains that gold miners woke up thinking it was morning and started making breakfast. People in the northeastern United States read newspapers by aurora light. Compasses at sea failed. Ships got lost. And this was in 1859, when the only electrical technology humans had was the telegraph. Carrington saw the flare at 11:15 in the morning Greenwich time. The Kew Observatory magnetometer recorded what scientists now call a magnetic crochet. Then nothing. Everyone went to bed. Then at 2:44 in the morning on September 2nd, the real storm arrived. Telegraph systems across Europe and North America went down. But here's the strangest part. Some operators disconnected their batteries entirely, and the telegraphs kept working. In Boston, an operator told his counterpart in Portland, Maine to cut off the battery. Both disconnected their power, and they had this conversation, transmitted entirely by the electrical current induced by the storm itself. The Portland operator said it worked better than with batteries on. If you value documented space weather and infrastructure history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. The script is researched and factual, using sources from the National Academy of Sciences report on geomagnetic storm impacts published in 2008. The Journal of Space Weather and Space Climate peer-reviewed analysis from March 2022 mapping the Quebec blackout, and British Geological Survey measurements from November 2025 documenting the largest geoelectric field since their records began in 2012. Now back to the information. The Carrington event traveled from Sun to Earth in 17.6 hours. Most coronal mass ejections take 3 to 5 days. This one was fast because another CME had cleared the path 2 days earlier on August 29th. Think of it like a snowplow. The first eruption pushed aside the ambient solar wind plasma. The second one raced through empty space at speeds approaching 2 million miles per hour. When it slammed into Earth's magnetosphere, it carried billions of tons of electrically charged plasma threaded with twisted magnetic field lines. And when those magnetic fields connected with Earth's own field, something terrifying happened. The fields merged, reconfigured, and released energy. The aurora that night reached 25 degrees geomagnetic latitude on August 28th through 29th, then 18 degrees on September 2nd through 3rd. That's Cuba. That's Hawaii. That's Colombia. Reports came in from within 23 degrees of the geomagnetic equator in both hemispheres. The sky glowed blood red, crimson, so bright you could read by it for hours. The glow came from oxygen atoms high in the atmosphere, getting hammered by charged particles. Red light means the particles penetrated deep, very deep, below 200 kilometers altitude, where oxygen is dense enough to emit that signature red wavelength at 630 nanometers. But the pretty lights weren't the problem. The problem was invisible. When Earth's magnetic field gets compressed and twisted by the impact of a coronal mass ejection, it generates an electric field at the surface, voltage per kilometer, usually 0.001 volts per kilometer. Tiny, negligible. During the Carrington event, estimates put it much higher. During the March 1989 Quebec storm, the Kew Observatory trace went off scale. During the November 12, 2024 storm, the British Geological Survey recorded 3.5 volts per kilometer in the Shetland Islands off Scotland. That's 3,500 times normal. And it had never been recorded before in their dataset going back to 2012. 3.5 volts per kilometer doesn't sound like much, but multiply that across hundreds of miles of transmission lines. High voltage power lines act like antennas. They couple to the geoelectric field through multiple ground points. The current that gets induced is quasi-direct current, 0.01 to 0.001 Hertz, compared to 60 Hertz alternating current in the power grid. That's basically DC. And DC current does something very specific to transformers. It saturates them. Here's how transformer saturation works. Power transformers have a magnetic core made of steel laminations. Alternating current at 60 Hertz creates alternating magnetic flux in the core. The steel handles this fine. It's designed for it. But when you add a DC component, even a small one, the magnetic flux no longer oscillates symmetrically around zero. It shifts. The positive half of the AC cycle pushes the core toward saturation. The magnetic domains in the steel all align. The core can't hold any more flux, so the flux spills out, stray flux. It escapes the core steel magnetic circuit and heats everything nearby. Copper windings, structural steel, tank walls. The transformer draws massive reactive power. Harmonics flood the system. Even harmonics. Second harmonic, fourth harmonic. The AC waveform gets distorted. At 2:44 in the morning, Eastern Time on March 13th, 1989, geomagnetically induced currents hit the Hydro-Quebec power grid. The James Bay network has very long 735 kilovolt transmission lines. Extra high voltage. The longer the line and the higher the voltage, the lower the resistance per kilometer. Lower resistance means larger induced currents. Quebec sits on the Canadian Shield, Precambrian igneous rock, highly resistive. The rock doesn't conduct electricity well, so the induced current found a better path. The transmission lines themselves. 5 static VAR compensators tripped within 1 minute. These are devices that stabilize voltage by injecting or absorbing reactive power. When the transformers started saturating, they consumed reactive power like they were starving. The compensators tried to compensate. They overloaded. They tripped. Voltage on the Lagrange network dropped to 0.2 per unit. 20% of normal, that's a catastrophic voltage collapse. 5 lines from James Bay to Montreal lost synchronism. A virtual fault. The entire network separated. 9,450 megawatts of generation gone in under 90 seconds. Total load was 21,350 megawatts. The system couldn't withstand the loss. It collapsed. 6 million people. No power. 9 hours. Temperature outside was minus 15 Celsius. Heating systems failed. Traffic signals went dark. Airports shut down. And the damage wasn't limited to Quebec. The New York power pool lost 150 megawatts the moment Quebec went down. The New England power pool lost 1,410 megawatts. A generator step-up transformer at the Salem nuclear power plant in southern New Jersey overheated and failed. That transformer cost $10 million. Within minutes of the storm beginning, over 200 grid faults erupted across the United States from coast to coast. Operators managed to shunt around most of them. The U.S. avoided major blackouts, but only barely. The March 1989 storm was rated KP8 on the geomagnetic storm scale. That's the second highest level. KP9 is the maximum currently defined. On March 24th, 1991, a KP9 storm hit. GIC measurements in transformer neutrals peaked at negative 200 amps. That's the neutral measurement. Each phase conductor carried about 67 amps of quasi-DC current, enough to drive transformers into half-cycle saturation, enough to generate stray flux that melts copper windings, enough to create hotspots that burn through insulation. High-voltage transformers aren't like the transformer on a telephone pole. They're enormous. They weigh hundreds of tons. They take months to manufacture. Many are custom-built. Most are made overseas. If a Carrington-level storm hit today and destroyed dozens or hundreds of extra high-voltage transformers across North America, the replacement time would be measured in years. Not weeks, not months, years. And during that time, large sections of the grid would stay dark. A 2008 National Academy of Sciences report estimated that a Carrington-level event today could cause $1 to $2 trillion in economic damage. That's not counting the cascading failures. No power means no refrigeration, no water pumping, no sewage treatment, no fuel pumps, no internet, no cell phones, no traffic lights, no hospital equipment. Modern civilization runs on electricity. Take it away for weeks or months, and you're looking at societal collapse in affected regions. But here's what makes solar storms truly strange. The mechanism that fries our technology isn't the radiation. It's not the heat. It's not even the particles directly. It's the magnetic field disturbance creating ground currents that our own infrastructure turns into a weapon against itself. We built an antenna network that perfectly couples to geomagnetic disturbances, 80,000 miles of extra high voltage transmission lines in the United States, over 200,000 miles across North America, Every mile of conductor acts as part of the antenna. Every grounded transformer neutral is an entry point for induced current. The Halloween storms of October 2003 registered the most powerful solar explosions ever recorded. Multiple X-class flares, X17, X28, before the sensors saturated. CMEs traveling at over 2,000 kilometers per second. When they hit Earth, transformers in South Africa got damaged. A city in Sweden suffered a blackout, leaving 50,000 people without power. In China, transformers at the Lingao nuclear power plant vibrated and made noise from the induced currents. In Russia, railway signals reported false blockages for hours. The Trans-Alaska pipeline was also affected. Engineers found that the pipeline degrades faster than expected because frequent ground currents at high latitudes accelerate corrosion. And then came May 2024. Between May 10th and May 11th, the Sun released what scientists later named the Gannon solar storm after deceased space weather scientist Jennifer Gannon. It was the most powerful solar storm in 20 years. 5 separate coronal mass ejections, multiple X-class flares including an X 5.1. The CMEs merged in space. When they arrived at Earth, they triggered a G5 geomagnetic storm. At the highest level, GPS went haywire, not just off by a few feet, off by 230 feet during the worst moments. GPS signals travel through the ionosphere. The ionosphere is a layer of charged particles in the upper atmosphere. Solar storms inject massive amounts of energy into the ionosphere. The particle density spikes, the electromagnetic properties change, GPS signals get delayed, refracted, scattered, the timing gets thrown off, and GPS relies on nanosecond precision. Light travels 1 foot per nanosecond. If the timing is off by even a tiny amount, the position calculation goes wrong. Farmers in the American Midwest were in the middle of planting season, peak planting season. 70% of planted acres in the United States use GPS-guided equipment. Tractors that drive themselves in perfectly straight rows. Planters that follow strip-till lines with 1-inch accuracy. Real-time kinematic GPS systems, RTK. These systems use ground-based correction stations to achieve centimeter-level precision. They need it. When you plant corn, you need to come back months later with a harvester and drive down the exact same rows. If you're off by even a few inches, you damage plants. You lose yield. You lose money. On Friday, May 10th, farmers started getting warnings. GPS accuracy extremely compromised. By Saturday, tractors were acting possessed. Kevin Kenny, a farmer in Nebraska, said, "All the tractors are sitting at the ends of the field right now, shut down because of the solar storm. No GPS. We're right in the middle of corn planting." Dennis Wolf in South Dakota reported his tractor going in circles. Auto steer didn't work, couldn't engage it. Elaine Ramstad, an Aurora chaser and farmer, said our tractors acted like they were demon-possessed. Her GPS was off by close to a foot. Twice the tractor danced a row to the left, to the right. The defoliator ended up off a row. She had to loop around and start over. John Deere dealerships sent out urgent messages. Landmark Implement warned that fields planted during times of reduced accuracy would have problems at harvest. The rows won't be where the autopath lines think they are. Making autopath work in these fields will be difficult, if not impossible, because the inaccuracy is most likely inconsistent. Translation: if you planted during the storm, you're going to have a nightmare trying to harvest. Rows will be crooked, overlapped, gapped. Equipment won't line up. Yields will suffer. The disruption lasted up to 2 days in some regions. The peak chaos was about 6 hours on May 10th. GPS errors up to 30 feet persisted during the auroral displays that followed. And this wasn't just a technical glitch. This was money. Real money. Terry Griffin, a professor of agricultural economics at Kansas State University, calculated the cost. Over $500 million in losses to American farmers. Planting got delayed. Equipment sat idle. Some farmers planted during the disruption and will face harvest problems. $500 million, and it wasn't just farmers. Aircraft rely on GPS for navigation, especially for knowing precise altitude during landing. Errors up to 4 meters can be compensated for. The May 2024 storm exceeded that tolerance window. Way beyond it, according to Nishimura, one of the researchers studying the event. Flights over polar regions during geomagnetic storms can experience radio blackouts, equipment disruptions, navigation problems. Satellite systems get affected. Communication satellites, GPS satellites, weather satellites. The charged particles can damage electronics, bit flips in memory, latch-ups in circuits, solar panels degraded by radiation. If you value documented infrastructure vulnerability and economic impact research like this, subscribe. This script uses sources from Terry Griffin's economic analysis at Kansas State University, published June 2024 in Farm Progress. The Space Weather Journal study by Nishimura and colleagues published June 2025, analyzing GPS disruptions during the Gannon storm. And the 404 media investigation from May 2024 with direct farmer accounts and John Deere dealership communications. Now back to the information. Here's what makes this even more unsettling. We're approaching solar maximum. The sun entered its latest solar maximum phase in October 2024. Solar maximum is when the sun's 11-year activity cycle peaks. More sunspots, more magnetic field complexity, more flares, more coronal mass ejections. The current cycle is expected to peak through 2025 and into 2026. Scientists can only determine the exact month of solar maximum at least 7 months after it occurs, but all signs point to right now being a dangerous period. On November 11th, 2025, the sun released an X 5.1 class flare from active sunspot region AR 4274, the strongest solar flare of 2025, massive radio blackouts across Africa and Europe. A series of coronal mass ejections followed, traveling at nearly 4.4 million miles per hour, 1,800 kilometers per second. They hit Earth's magnetic field on November 12th, G4 class geomagnetic storm. The aurora was visible as far south as northern Alabama. An X-class flare released on November 12th created the largest solar particle storm since 2005, according to the British Geological Survey. The largest measured geoelectric field since their records began in 2012. 3.5 volts per kilometer in the Shetland Islands. That value had not been recorded before in their entire data set. Blue Origin had to postpone a launch. The Escapade spacecraft couldn't launch because of highly elevated solar activity and its potential effects. Space weather conditions had to improve first. NASA and Blue Origin were monitoring closely. This is what solar maximum looks like. This is the environment we're in right now. And here's the truly frightening part. The Carrington event was twice as big as any other solar storm in the last 500 years. We know this from ice core samples. When geomagnetic storms hit, they trigger high amounts of cosmic rays in Earth's upper atmosphere. The cosmic rays produce carbon-14, radioactive carbon. Scientists drill ice cores from Greenland and Antarctica. They measure carbon-14 levels in annual layers going back thousands of years. The Carrington event shows up, clear spike, but it's not the biggest. Around 774 AD, something happened. The Miyake event, named after the scientist who discovered it, a solar storm at least 10 times stronger than the Carrington event. The carbon-14 spike in ice cores is massive, the fastest rise ever recorded. Another Miyake event occurred around 993 AD. 60% smaller than 774, but still enormous. These events happen roughly once every 400 to 2,400 years, based on one study. Another study looking at tree rings in the French Alps found evidence of the largest solar storm ever recorded, 14,300 years ago. 7 Miyake events have been identified in the past 15,000 years. Research on sun-like stars in space indicates that superflares far larger than the Carrington event may occur every few hundred years. We're overdue, and our dependence on technology has never been greater. In 1859, the telegraph was the only vulnerable technology. In 1989, we had power grids and some satellites. In 2024, our entire civilization runs on GPS, satellites, power grids, internet, communications networks, digital control systems, just-in-time, supply chains, electronic banking, and infrastructure that assumes electricity will always be available. A Bloomberg intelligence report from May 2024 warned that a major space storm could cost insurers more than Hurricane Katrina. Katrina caused $55 billion in damage in 2005. That's $90 billion in today's dollars. The geomagnetic storm could exceed that, given its potential to disrupt radio communications, power grids, spacecraft, and satellite navigation across entire continents simultaneously. The probability of a storm like the March 1989 Quebec incident occurring somewhere in the world is about once every 70 years, according to Allianz risk experts. We're 35 years past Quebec. We're halfway to the next expected event, and that's just Quebec level. Carrington-level events are less frequent but far more destructive. The National Oceanic and Atmospheric Administration uses satellites to monitor the sun. The Geostationary Operational Environmental Satellite System, GOES. These satellites observe solar flares and CMEs. They provide early warning, but the warning time is limited. Solar flares travel at light speed, 8 minutes, no warning possible. CMEs take 15 hours to several days depending on speed. That's your window. 15 hours to several days to prepare for potential grid collapse. What can you do in 15 hours? Utilities can take some action. Reduce load on the most vulnerable transformers, open certain transmission lines, increase reserves, but there's only so much you can do. The grid is interconnected, complex, rigid in some ways. You can't just turn it off and turn it back on. Black start procedures after a major blackout take days even under the best conditions. If transformers are damaged, it takes months or years. In 2013, it's on. The Federal Energy Regulatory Commission ordered the North American Electric Reliability Corporation to create standards. Power grids must be protected from solar storms. Equipment must be tested. Utilities must develop operating procedures for severe geomagnetic storms. The final rule was published in September 2016. Better late than never. But the standards are based on historical storms. What if the next one is bigger? What if it's Carrington level? What if it's Miyake level? The mechanism is well understood now. Magnetic reconnection on the sun releases energy. Coronal mass ejection accelerates plasma to millions of miles per hour. The plasma carries twisted magnetic field lines. CME travels through space, impacts Earth's magnetosphere. Magnetic fields merge and reconfigure. Energy dumps into the magnetosphere and ionosphere. Charged particles stream down magnetic field lines. Aurora appears. Particles create ionospheric currents. Ionospheric currents create changing magnetic fields at ground level. Changing magnetic fields induce electric fields. Surface geoelectric field drives current through ground. Ground currents find path of least resistance. Transmission lines. Current enters grid at transformer grounds. Quasi-DC current flows through transformer windings. Magnetic core saturates. Stray flux heats components. Harmonics flood system. Reactive power consumption spikes. Voltage collapses. Protective relays trip. Cascade begins. Each step is physics. Faraday's law, Ampere's law, Ohm's law, magnetic field behavior, electromagnetic induction, power grid engineering. It's all textbook stuff. But when you chain it together across 93 million miles and through systems designed by thousands of engineers who never imagined the sun could reach out and touch their work, you get emergent behavior. You get a continental scale antenna tuned to receive geomagnetic disturbances and convert them into grid-destroying currents. And GPS disruption adds another layer. Modern farming is precision agriculture. Variable rate application, yield mapping, strip tillage, GPS-guided planters, sprayers, harvesters. Remove GPS and you remove efficiency. You remove yield, you remove profitability. 80% of Midwest farmers use GPS for something. 50% are very reliant on it, according to John Deere service manager Ethan Smith. 20 years ago, if a solar storm hit, farmers wouldn't have cared. They didn't use GPS. Now, automation means solar storms are nightmares. The ionosphere extends from about 50 kilometers to 1,000 kilometers altitude. GPS satellites orbit at 20,000 kilometers. The signals pass through the ionosphere. Normally, the ionosphere is relatively stable. Electron density follows predictable patterns. Day-night cycle, seasonal variations, solar cycle variations. GPS receivers compensate for these. But during a geomagnetic storm, the ionosphere becomes turbulent. Electron density fluctuates wildly. Scintillation, signals fade, timing errors accumulate, the position solution drifts. RTK GPS uses ground stations to send correction signals. The ground stations know their exact position. They measure the GPS error at their location. They broadcast corrections. Your receiver applies the corrections. You get centimeter accuracy, but the correction signals use radio frequencies. During geomagnetic storms, radio propagation gets disrupted. The correction signals get degraded or lost. Without corrections, you're back to standard GPS accuracy. Meters, not centimeters. For precision agriculture, that's useless. The May 2024 storm hit during the midnight hours in the US. Farmers often work at night during planting season. Long days, long nights. GPS lets you plant in the dark. But when GPS fails in the dark, you're stuck. You can't see where you're going. You can't use visual landmarks. You can't plant. So you sit at the end of the field and wait for morning, or wait for the storm to pass. Every hour of delay matters. Weather windows close. Soil conditions change. Planting deadlines approach. Miss your window and your yield suffers all season. The aurora during the May storm was visible in Utah, in Ohio, in Mexico, in Puerto Rico. The G5 rating means extreme geomagnetic storm. Power systems experience voltage control problems. Protective devices trip. Spacecraft experience surface charging, GPS degraded for hours, high-frequency radio propagation impossible in many areas. And this was just one storm. Active region AR4274 continued producing flares. There's a 40% chance of another X-class flare in the coming days, according to ESA's Space Weather Office after the May storm. Same thing happened in November 2025. AR4-274 again, multiple X flares, multiple CMEs. Solar maximum is a dangerous time. The sun's magnetic field becomes entangled, twisted, stressed, like rubber bands wound too tight. Eventually they snap. The snap releases energy. The energy accelerates plasma. The plasma travels to Earth, and our technology pays the price. Every solar maximum brings increased risk. This one is no different. The peak might last through late 2025 or into 2026. We're in the danger zone now. Engineers are working on solutions. For power grids, the main defense is blocking DC current. Install capacitors in series with transformer neutrals. Capacitors block DC but pass AC. Simple concept. Expensive to implement across thousands of transformers. Hydro-Quebec installed such systems after 1989. They've avoided major blackouts and subsequent storms. Other utilities are following, slowly. Another approach is better monitoring. Measure GIC in real time at critical transformers. Measure second harmonic. That's the signature of saturation. If second harmonic spikes, you know a transformer is saturating. You can take action, shed load, reroute power, anything to reduce the stress. The U.S. Geological Survey operates 14 ground-based magnetic observatories across the United States and territories. Some have run continuously for over 100 years. They monitor Earth's magnetic field. They provide data to utility companies, geoelectric hazard maps, vulnerability assessments, mitigation strategies. For GPS, the fixes are harder. You can't block solar storms from affecting the ionosphere. You need backup navigation, inertial navigation systems, visual systems, machine learning. AI-driven guidance that doesn't rely solely on satellites. Engineers are exploring these, but implementation takes time and money, and the agriculture industry operates on thin margins. Investing in backup systems that you might need once every few decades is a hard sell. For satellites, radiation hardening helps, shielding, redundant systems, error correction. The GOES satellites sit at 22,300 miles altitude, outside Earth's protective magnetic field. They need extra protection. They have systems of gradually darker filters. Sunglasses for satellites. They can handle the radiation. They have to. They're the ones watching for storms. If they fail, we're blind. But none of this eliminates the risk. It only reduces it. A true Carrington event would overwhelm protections. A Miyake event would be catastrophic. And we can't predict them precisely. We can see active regions on the sun. We can watch for CME launches. We can track them through space. But we can't predict the exact magnetic field orientation. We can't predict the exact speed. We can't predict the exact impact angle. All of these affect how much energy couples into Earth's magnetosphere. The magnetic field of a CME matters enormously. If the CME's magnetic field is oriented southward when it hits Earth, it couples efficiently with Earth's northward field. Maximum reconnection? Maximum energy transfer? If it's oriented northward, it doesn't couple well. Minimal effect, but the field can rotate during transit. We only know the orientation when the CME passes the DS Cover satellite at the L1 Lagrange point. L1 is 1.5 million kilometers from Earth toward the Sun. Light travel time from L1 to Earth is about 5 seconds. Particle travel time is 15 minutes to an hour depending on speed. That's your final warning. 15 minutes to an hour. What do you do with 15 minutes warning? Alert utilities. They can try to stabilize the grid. Alert airlines. They can reroute polar flights. Alert satellite operators. They can put satellites in safe mode. Alert GPS users. Farmers can stop planting, but you can't prevent the storm. You can only brace for impact, and the social implications are staggering. Imagine a Carrington event hitting today. Imagine transformers burning out across North America. Imagine weeks or months without power in major cities. New York, Chicago, Los Angeles, Toronto, Montreal. Refrigeration fails, food spoils, water treatment plants stop, sewage backs up. Hospitals run on generators until fuel runs out. No internet, no cell service, no ATMs, no credit cards, no gas pumps, no supply trucks. Society depends on just-in-time delivery. 3 days of food in most grocery stores. 3 days, after that, shelves empty. And they don't refill if trucks can't move. Economic damage in the trillions? Yes, but the real damage is social breakdown, panic, looting, violence. Governments would struggle to maintain order. Emergency services would be overwhelmed. And all because the sun had a tantrum and our technology couldn't handle the result. This isn't alarmist speculation. This is sober risk assessment based on historical events and modern infrastructure vulnerability. The National Academy of Sciences said it, Allianz said it, NOAA said it. FEMA is paying attention. The Department of Homeland Security considers geomagnetic storms a national security threat, but public awareness remains low. Most people don't know what a CME is. They see pretty auroras and take photos. They don't realize the aurora is a symptom of the same process that could kill the power grid. They don't realize their GPS is vulnerable. Their satellites are vulnerable. Their entire technological civilization is vulnerable. And the threat comes from a natural process 93 million miles away that we can barely predict and cannot stop. So what happens next? We continue to watch the sun, we improve forecasting, we harden infrastructure, we develop backup systems, we educate the public, we train emergency responders, we stockpile critical equipment, we develop rapid response capabilities, we learn from 1989, we learn from 2003, we learn from May 2024, we learn from November 2025. And we hope we're ready when the big one comes. Because the big one is coming. Maybe not this year, maybe not this decade, but the statistics are clear. Miyake events happen. They happen roughly once every few centuries. We're within the window. And with each passing year, our dependence on vulnerable technology increases. The irony is brutal. The more advanced we become, the more fragile we become. The more we rely on satellites and GPS and power grids and digital systems, the more a natural phenomenon can destroy our way of life. We've built a house of cards, and the wind is blowing. The strange part isn't that the sun threatens us. Stars do that. The strange part is that we built our entire civilization on systems exquisitely tuned to be vulnerable to something we knew was coming. Engineers in the 1800s saw telegraph systems fail during storms. They didn't understand why. Engineers in 1989 saw transformers saturate. They understood the mechanism. They wrote papers about it. But implementing fixes costs money, and the storms are rare. So the fixes come slowly, if at all. The risk assessment is clear. The mechanism is understood. The vulnerability is documented. But action is inadequate, because the cost of prevention is certain and immediate. The cost of inaction is uncertain and delayed. This is human nature. This is how societies fail, not because we don't know the threat, but because we choose not to act until it's too late. Quebec went dark for 9 hours. They fixed their grid, installed protections, spent money. The rest of North America mostly didn't. Why? Because Quebec got hit and they didn't. It won't happen to us, and if it does, we'll deal with it then. This is the logic that fails when the transformer melts and the replacement takes 18 months to manufacture and ship from overseas. This is the logic that fails when GPS is down for 2 days and $500 million in agricultural productivity evaporates. The sun doesn't care about our logic. The sun doesn't care about our economy. The sun doesn't care about our infrastructure. The sun follows physics. Magnetic fields twist, they store energy, they release it, plasma accelerates, it travels, it impacts, and we either prepare or we suffer. Scientists studying the November 2025 storm found something that hadn't been recorded before. 3.5 volts per kilometer in the Shetlands. New record. The British Geological Survey has monitored geoelectric fields since 2012. In 13 years, they'd never seen anything like it. And that wasn't even a Carrington-level event. That was just a strong storm during solar maximum. Imagine what Carrington level looks like in their instruments. The Carrington event telegraph disruptions lasted hours. Operators worked around them. Some sent messages using auroral current. The outage was interesting. Annoying, maybe. But not catastrophic. Because in 1859, civilization didn't depend on electricity. Today it does. Today we have 80,000 miles of transmission lines waiting to act as antennas. We have thousands of transformers waiting to saturate. We have millions of GPS receivers waiting to give bad coordinates. We have satellites in orbit without ground backup. We have supply chains optimized for efficiency, not resilience. We have cities with 3 days of food. We have populations that don't know how to function without electricity. This is the world a Carrington event would hit. This is the world a Miyake event would destroy. Not destroy physically. The buildings would still stand. The roads would still exist. But destroy functionally. Destroy economically. Destroy socially. Because modern civilization is not the buildings and roads. It's the electricity and data flowing through them. Cut the flow and the civilization stops. And the mechanism remains strange. Not fire from the sky, not an asteroid impact, not a nuclear war. Just magnetic fields doing what magnetic fields do. Just plasma following field lines. Just induced currents in long conductors. Just transformers saturating. Just GPS signals getting delayed. Simple physics. Basic electromagnetics. Nothing exotic. Nothing theoretical. Just well-understood processes that happen to combine in a way that threatens everything we've built. A recent study published in June 2025 analyzing the Gannon storm found GPS receivers were off by up to 230 feet during peak disruption. The disruption lasted for about 6 hours at peak intensity. but unsettled conditions persisted for up to 2 days. After the ionosphere began to calm, the auroral displays caused further disruptions. GPS errors up to 30 feet continued as charged particles trickled through the atmosphere along disrupted magnetic field lines. This is what moderate solar storms do. This is what we experienced in May 2024, and it cost $500 million in agricultural losses alone. Scale that up to Carrington level, scale it up to Miyake level, the numbers become incomprehensible, the impacts become civilization ending, and the probability is non-zero. Ice cores don't lie. Tree rings don't lie. The evidence is clear. These events happen. They will happen again. The question is when, and are we ready? The answer to are we ready is no. We're not ready. We're making progress. We're installing some protections. We're improving forecasting. We're raising awareness, but we're not ready. A Carrington event tomorrow would cause catastrophic damage. A Miyake event would be apocalyptic, and we're in solar maximum right now. The risk is elevated. The sun is active. Sunspots are numerous. Flares are frequent. CMEs are launching, some toward Earth, some away. We watch. We wait. We hope the big one misses, but hope is not a strategy. Hope is what you do when you don't prepare, and we're not preparing fast enough. The engineers know. The scientists know. The government knows. The insurance companies know. But knowing doesn't fix transformers. Knowing doesn't harden GPS. Knowing doesn't stockpile critical equipment. Knowing doesn't build resilience. What fixes transformers is money and political will. What hardens GPS is engineering and deployment. What stockpiles equipment is logistics and planning. What builds resilience is taking the threat seriously and acting before disaster strikes. But that requires accepting cost and inconvenience now to prevent catastrophe later. It requires thinking beyond quarterly earnings and election cycles. It requires long-term vision and sustained effort, all things human societies struggle with. So we remain vulnerable, and the sun remains active, and the magnetic fields keep twisting. And someday they'll snap in just the right way, pointing just the right direction, moving just the right speed, and the plasma will hit Earth's magnetosphere with maximum energy transfer. And the geoelectric field will spike to levels we've never measured, and the currents will flow through our carefully built antenna network, and the transformers will saturate and overheat and fail, and the GPS will give coordinates that are wrong by hundreds of feet or stop working entirely. And the satellites will get damaged, and the power will go out, and it will stay out for a long time, in a lot of places, and we'll wish we had prepared better. Ice core analysis from Greenland samples drilled in 2022 showed the 774 AD Miyake event produced a carbon-14 spike that rose faster than any other in the 15,000-year record. The spike happened over a single year, maybe over months. That's how fast the storm was. That's how intense it was. 10 times the Carrington event. The aurora would have been visible at the equator. The geoelectric field would have been enormous. If telegraph systems had existed in 774, they would have melted. We don't have records of what happened on the ground in 774, no written records of aurora, no accounts of strange phenomena, just the ice core spike and tree ring evidence. But we can model it. We can calculate the impact on modern infrastructure. The models are not encouraging. They show continent-scale blackouts lasting months. They show transformer damage so extensive that repair is measured in years. They show GPS unavailable for days. They show satellite damage across multiple constellations. They show supply chain collapse. They show humanitarian crisis. And they show that we're not ready. Not even close. We've taken baby steps toward resilience, installed a few protections, written a few regulations, improved a few forecast models, but we haven't made the systemic changes needed to survive a Miyake event. And maybe that's rational. Maybe the cost of preparing for an event that happens once every 500 years is too high. Maybe it's better to take the risk and rebuild afterward if needed, but that calculation assumes rebuilding is possible. It assumes society holds together during the crisis. It assumes international cooperation continues. It assumes supply chains can be restored. It assumes critical knowledge isn't lost. All big assumptions. And history shows that societies under stress don't always hold together. They fragment, they collapse, they lose capabilities. The Roman Empire fell. The Bronze Age civilizations collapsed. Easter Island civilization destroyed itself. It can happen. It does happen. And a sufficiently large infrastructure shock could trigger it. This is the ultimate strangeness of solar flares frying our technology. The threat isn't alien. It's not malicious. It's not even aimed at us. It's just the sun doing what stars do, releasing magnetic energy. And we happen to live close enough to be affected. And we happen to have built our civilization on technology that's vulnerable. The universe is indifferent. Physics is indifferent. The sun will keep making flares. The plasma will keep traveling. The magnetic fields will keep reconnecting, and our transformers will keep saturating unless we protect them. Our GPS will keep failing unless we build redundancy. Our civilization will keep being vulnerable unless we make it resilient. The choice is ours. The sun will do what it does. We can either prepare or not. We can either accept the cost of protection or accept the risk of catastrophe. Both are choices. Inaction is a choice. And right now, we're choosing to remain vulnerable. And we're choosing to hope the big one doesn't come during our watch. We're choosing short-term comfort over long-term survival. That might work out. The probability of a Miyake event in any given year is low. The probability in our lifetime is still fairly low, but the probability over the next few centuries is high, and civilizations are meant to last centuries, millennia even. If we want our civilization to last, we need to protect it from known threats, and solar storms are a known threat, with a known mechanism and known solutions. We just need to implement them. But implementation requires facing an uncomfortable truth. We are not safe, we are not secure, we are not invulnerable, we are fragile. Our technology is fragile, our infrastructure is fragile. Our supply chains are fragile. Our society is fragile, and the things we depend on can fail. The power can go out. The GPS can stop working. The satellites can die. The transformers can melt. And when that happens, we're on our own, with whatever preparations we made or didn't make. This is the lesson of solar storms. This is the lesson of Quebec in 1989. This is the lesson of May 2024. This is the lesson of November 2025. The sun is not our friend. The sun is a massive fusion reactor, 93 million miles away, that occasionally throws tantrums. And we live in the blast radius. We always have. We always will. As long as we're on this planet, we're vulnerable to solar weather. We can't change that. But we can change how prepared we are. The strange reason the sun's flares can fry our tech is that we built the perfect receiver. We turned our power grid into an antenna. We made our transformers vulnerable to DC saturation. We made our GPS dependent on ionospheric stability. We made our satellites vulnerable to radiation. We did this, not the sun. The sun just does what it always did. We're the ones who built vulnerable systems and then put our entire civilization on top of them. And now we're in solar maximum. The sun is active. The risk is high. And we're mostly unprepared. We have some monitoring, some protections, some plans, but not enough, not nearly enough. And every day we delay is another day we roll the dice. Another day we bet that the big one won't come. Another day we hope luck holds. Luck doesn't hold forever. Eventually it runs out. Eventually the magnetic field points south. Eventually the CME is fast enough. Eventually the impact is direct enough. Eventually the storm is strong enough. And on that day, we'll learn whether we prepared enough, whether we took the threat seriously enough, whether we invested enough in resilience. The evidence from the Shetland Islands in November 2025 measured 3.5 volts per kilometer, largest on record since 2012, from a storm that wasn't even Carrington level. The British Geological Survey noted this value had not been recorded before. New territory, and not in a good way. Each strong storm seems to push the measurements into ranges we haven't seen before. Each storm is a warning, a reminder, a preview of what's possible. And what's possible is very bad. What's possible is grid collapse, transformer destruction, GPS failure, satellite damage, communication breakdown, supply chain disruption, social chaos, economic catastrophe, all from magnetic fields doing what magnetic fields do. All from plasma following physics, all from the sun having a bad day. This is the world we live in. This is the threat we face, not from enemies, not from terrorists, not from war, from nature, from the star we depend on for life. The same star that can take away the technology that makes modern life possible. The irony is cosmic. We are threatened by the thing that gives us life, and we're mostly ignoring the threat, until we can't anymore, until the next Carrington event hits, until the next Miyake event occurs. Until the transformers melt and the GPS fails and the power goes out, and stays out for a long time, across a large area, affecting millions of people, costing trillions of dollars, disrupting civilization. It's coming. Maybe not today, maybe not tomorrow, but soon. On cosmic timescales. And when it comes, we'll wish we had prepared better. We'll wish we had listened to the scientists. We'll wish we had spent the money. We'll wish we had taken it seriously. But wishes don't fix transformers. Wishes don't restore power. Wishes don't feed people. Only preparation does that. Only resilience does that. Only taking the threat seriously and acting on it does that. And right now, we're not doing that. Not enough. We're talking about it. We're studying it. We're writing reports. But we're not acting at the scale needed. Not yet. Maybe we will. Maybe the November storm scared enough people. Maybe the May storm cost enough money. Maybe the warnings are finally being heard. Or maybe we'll keep waiting, keep hoping, keep gambling, until we lose, until the sun reaches out 93 million miles and touches our technology with magnetic fields we can't stop, until the geoelectric field spikes, until the current flows, until the transformers saturate, until everything we depend on fails at once. That's the strange truth about solar flares frying our technology. It's not strange that it happens. It's strange that we let it happen. We know the mechanism. We know the vulnerability. We know the solution. We just choose not to implement it. And that choice might cost us everything.